In this video, we are going to be explaining the concept of quantum tunneling and its uses in modern-day physics. Quantum tunneling is an important concept which is included in the Atom, Stars and the Universe module of your course.
Quantum tunneling is important to understand as it's an important factor in many things such as nuclear fusion, chemical reactions and modern technology. There's even a theory that the entire universe may quantum tunnel from its current energy state into a lower energy state, but we'll save that for another video.
Tunneling is a quantum mechanical phenomenon in which a particle passes through a potential energy barrier that classically it could not surpass. Let's picture the classical scenario in which there's a particle with a fixed amount of energy, E. In front of this particle there is a potential barrier requiring energy, V, to pass over. If the energy of the particle is less than that of the potential barrier, then it will not pass to the other side. This is what happens in a classical scenario and is a simple idea to process. However, not all scenarios are classical, and this is where quantum mechanics comes into play. In the quantum scenario, even if a quantum particle has less energy than the potential barrier, there is a finite probability that the particle will be found on the other side. This behavior is called quantum tunneling. To explain this, we need to look at the wave function describing the particle. The wave function, psi of x, is defined such that the modulus of the wave function squared integrated between the limits a and b is equal to the probability of finding the particle in the space between x equals a and x equals b. This is called the Born rule.
One of the properties of a wave function is that both the wave function itself and its first derivative must be continuous. To understand the implications of this and how it gives a rise to quantum tunneling, let's look at an example wave function. Outside of the potential barrier, the particle has a sine wave function. Classical mechanics will predict that inside the potential barrier, the wave function must be zero, as it is impossible for the particle to surpass the potential barrier. However, if this was the case, it would violate the condition that the wave function must be continuous. Therefore, the particle approaches the quantum barrier, the probability of finding it there cannot be zero. Instead, the wave function of the particle inside the barrier exponentially decays, such that if the barrier is sufficiently narrow, there is a probability of finding the particle on the other side.
This is possible due to Heisenberg's uncertainty principle. The limit to the precision with which we can measure a particle's position imposed by Heisenberg's principle means there's a chance the particle could be viewed on the other side of the barrier, as if it had tunneled through.
Let's take a look at the equations explaining this scenario. We have a particle with energy E and a potential barrier with energy V. If E is significantly less than V, then the probability, P, of the particle passing through the barrier can be calculated with the following equation. P equals e to the power of minus 2Cl.
If you're struggling to visualize the process of quantum tunneling, not to worry. Here's a scenario entirely analogous to quantum tunneling which you can perform at home. You can see the glass of water being viewed from above. We're viewing the glass at above the critical angle for the glass to air boundary, so light is being totally internally reflected from the glass into our eyes. It therefore does not pass into the air, and so does not reflect off the fingers behind the glass. That is why you can't see them, even though you know they're there. However, there is in fact a small amount of light crossing the glass to air interface, but its amplitude exponentially decays with distance, just like our quantum particle tunneling through the potential barrier. Therefore, we can't see the fingers if they're too far away from the back of the glass. However, if the fingers are moved closer to the back of the glass, the amplitude of light reflecting off them is sufficient for you to now see the fingers. Photons are essentially quantum tunneling across the glass-to-air interface, allowing the fingers to become visible. Now we understand the theory behind this, let's look at a physical application of this phenomenon. Scanning tunneling microscopes are very precise tools for measuring surfaces. As we've previously seen, the probability of a particle tunneling through a barrier is P equals e to the power of minus 2Cl. A current, consisting of electrons, is passed through the microscope where it reaches a potential barrier between the electrode tip and the surface of the material. As the probability of quantum tunneling of the electron, and thus probability of a current flowing, depends on the distance L between the electrode tip and the surface, the measured current can be used to determine the distance to the surface of the material. These distances can be used to construct an incredibly precise 3D model of the material to produce an image such as this one of the surface of gold.
We hope you found this video interesting and useful, and wish you the best of luck studying the Atoms, Stars and the Universe course at UCL. Thank you for watching.